C4, you have a cyclic group of order 4, or it's of this form, the direct product C2 by C2. Okay? So that's the classification of G4. When there are only two kinds of group. Okay. Now for G6, that's the next possibility. So we've done now 2, 3, 4, 5. So the next one is 6. So now I'm talking about G6. So again, let's use this very powerful result. The order of the element divides the order of the group. Okay? So we're talking about G6. So what are the possible orders of an element, little g, belonging to big G, the group? Now, forget the trivial one. That's always the case. There's E. It's a trivial subgroup. It's and one of the two improper subgroups, right? So forgetting the unit. The factors are, other than 1, for 6, 2, 3, and 6. Okay. So let's where we start. Well, in the text, let's assume that they're all the non-unit elements. Let's say they all have order 2. Okay? So we have 3 elements, and each is of order 2. Now, if that's the case, there was a theorem we did. In fact, it's here. It's the same one. Theorem 38, and that theorem says that if every member except the unit is of order 2, then that group is isomorphic to this. So you'll have a cyclic 2 for each element. We've got 3 elements of order 2. But the order of this group is 2 by 2 by 2. That's 8. So that's contradiction, because we only have order 6. So you cannot have all of those 3 elements having order 2, because if that were the case, then the group would be isomorphic to that. But then you've got a problem, because the order of this group is 2 by 2 by 2. That's 8, but the order is 6. So we can eliminate the possibility that all 3 of your non-unit elements are of order 2. That cannot be, right? So therefore, we must have a mix, of order 2 and order 3, except if we do have one order that's 6. Now, if one of these elements, little g, if its order is 6, that's okay, that's a factor, right? If it's 6, then that means that g here, by definition, is a generator, right? Because it generates the whole group. Because g to the 6th is then E. So that means G6 is then the cyclic group of order 6. Right? Now remember me saying that's true for any integer n. You'll always have the cyclic group. So if we do have one of these elements has order 6 or more, if one element or more has order 6, then we have the cyclic group. Okay? So we've found one, at least, of order 6. It's the cyclic group. Alright? So let's eliminate that possibility. So now we're considering the possibility that there are no elements of order 6. So that only leaves 3 and 2. Okay? So let's just say element A is the element that has order 3. Okay? So we'll assume that. And that we have no order 6 element. Right? We've already done that. We've eliminated that possibility. Because if there is an element of order 6, the group's cyclic. and we've done that. So now we're looking for different types of groups, non-isomorphic groups. So and they can't all be 2, so there has to be an order 3 in there somewhere. Okay, so let that element of order 3 be A. So, all right. All right. So now, if the order is 3, and so here's your subgroup generated by that element. So E, A squared, right? And that's a subset. We did a theorem on that way back. So that's a subset of G6. Okay, so those 3 elements belong to G6. Now, so we now have half of the elements of G6. So we don't know what the 4th one is, but let it be B. And it's distinct from these 3, right? I mean, if B is one of these 3, then it's not another element. We've already got these 3. So let B be a 4th element different from these 3. So B is not one of these 3. Okay? It's a distinct. It's a different element. It's a 4th element. Now, because of closure, we're talking about a group. So if B is a distinct element, then you can multiply. You can have a binary operation in your group table between B and A, right? So BA will be, by closure, will be a member of the group, and BA squared also will be a member of the group. So there are your six elements, all right? So A and B being generators, all right? So now let's. Here's where it really starts getting dense. You can just look at it. Now let's try to fill in the group table. Right. So we've now got our 6 members. So we can start making deductions about the table, because if we know the table, we know the group. Right? The group table tells us everything there is to know about a group. If you have the group table, if you have all the elements in the group table, you have a total knowledge of the group. All right? Well, one of the elements in this group table will be BB. Right? So B is a member of the group of G6. So what is B squared? So see if we can try and figure out what B squared is. Well, could it be B or BA or BA squared? In other words, could it be one of these 3? Well, we can eliminate those possibilities, because if B squared does equal to B, and there's a lot of tight logical reasoning from now on, so pay attention. So we're trying to eliminate the idea that B squared is one of these 3. And so if B squared is B, then B is E, right? But that's not, so I put it across here, that meaning, eliminated, no good. Because we've assumed that B is a 4th element, it's different from E, okay? So that's out. Well, how about B squared is BA? Well, that implies that B equals A. So this one is equal to that one. But no, it's a 4th distinct element, so that's out, right? X. Well, how about B squared is BA squared? Well, that means B equals A. So B equals, B squared is BA squared. So B is A squared. So that would not be distinctive. So that's out. So where is it? B squared cannot be one of these 3. All right. So how about, could B squared be A here? Is that a possibility? Well, is B squared equal to A, question mark? Well, therefore, if you take A squared, this will be B to the 4th, right? Now A squared is not E, because A, we assumed the order was 3. Okay, so A to the 4th is not E. So how about A cubed? Yes, that's E. So A cubed is E. And so that's the first time the first power, the smallest power, positive integer of A that gives you E. By definition, right? That's the order of A, which we assumed was 3. So for the first time, when B goes to the power 6, does it become E? B to the 6 for the first time, when that power 6 becomes E. So that means, by definition, the 6 here is the order of B. Right? But we assumed no order 6 elements. Right? We're doing the cases where there's no order 6. So therefore B squared cannot be A, because if it is A, then B has order 6 out, right? Eliminated. So that's out. All right. So what does that leave? So no, 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 no. So let's try. Could B squared be A squared? Is that a possibility? Well, it's the same argument. If you take this, if you square A squared, you get A to the 4th. That's not E, right? So if you cube it, A to the 6th becomes E, because A cubed is E, right? And the first time A squared becomes E is when this is 6. So this is also 6. So the power here for the first time, as you go up, 2, 4, 6,